Alright, welcome back guys. We're going to look at section 9.6, and this is sort of the culmination of everything that we did in 9.5, working with those properties of logarithms, because we're going to be solving exponential and logarithmic equations. Okay, we'll start off solving exponential equations. So what makes an exponential equation? Well, you have to have a variable in the exponent's place, okay? And then it's an exponential equation for the most part. Now to do this, we're going to utilize this property right here, okay? So it says that if you have a to the x power, and that's equal to a to the y power, then this implies that those exponents have to be equal to each other. Okay? Otherwise, the left side's not going to be equal to the right-hand side. Now you may think, well, this is pretty trivial. Why are you talking about that? Well, we're actually going to utilize that in solving these exponential equations. And I'll show you how. What we're going to try to do, this is called, put this in the notes, equating the base. Okay? So you remember what the base is. The base in this case is a. So if I have an exponential equation like this example 1 here, where there's a variable, we have an x as the exponent, if I can somehow equate the bases, then I can equate the exponents. That's what this property says. Okay. Now you may say, well, equate the base, what do you mean? Well, the 25 here, I can rewrite this as an exponential expression because the base on the left-hand side is already 5. If I can re-express 25 as 5 to some power, then then the bases will be equal to each other, and so that will imply that the exponents have to be equal to each other. Okay, and so what I mean is this. Instead of writing 25, I'm going to express it using an exponent, using a base and an exponent. Okay, so 25, if you recall, is the same as 5 to the second power. Okay, and so by doing this, I have equated the bases. And so using this property up here, this then implies that this exponent has to be equal to this exponent. In other words, this implies that x has to be equal to 2. Okay. Now you may think, well, this was pretty simple. I could have just figured out by looking at this that x has to have a value of 2. Otherwise, it's not going to equal 25. Okay. But some of these are not so obvious. Okay, and so that's why we're going to try to equate the base. So there's actually, in solving exponential equations, there's two different methods. If you can equate the bases, then do so. But other times, it basically is impossible to equate the bases. And so there's another method involving logarithms that we have to employ to solve the equation. Okay, but we'll look at that here in a minute. This first method is called equating the base. So let's take a look at example 2 here. Example 2, we have 3 to the power of 2x, and this is equal to 27. So the base I'm going to be working with is 3, because I already have this. So I need to somehow re-express 27 as 3 to some power. Okay, well, if you recall, 3 to the second power is 9, 3 to the third power is 27. So we copy the left-hand side, and I'll express 27 as 3 to the third power. The nice thing about equating the base, guys, is you know what the base is. So you just try a few powers of 3, or whatever the base is that you're working with, until you find the value here that you're looking for. Okay, and so because the bases are equal, then this implies that the exponents have to be equal, that 2x has to equal 3. Okay, 2x here has to equal 3, And so once you arrive here at this step, you can solve, this will be a linear equation typically. You can solve for x by dividing both sides by 2, and you obtain x is equal to 3/2. So that's the value that solves this equation. And you can check these as well, guys. If you plug 3/2 back in here, 2 times 3/2 is 3. And 3 to the third power is equal to 27. Okay. Alright, let's try example 3. The last one where we'll be equating the base. So example 3 here, the base is 5, okay, and I've got this linear function in the exponent's place, 4x minus 7. So I need to somehow express 625 as 5 to some power. Well, I'm going to use the online calculator. Well, you just try 5 to a few powers. We know it's not 5 to the second. We try maybe 5 to the third. Oh, that's not 625. So we go up 1, 5 to the fourth. That is 625. Okay. So we're going to express 625 as 5 to the fourth power. And then this will equal the left-hand side, 5 to the power of 4x minus 7. And so again, because the bases are the same, this implies that the exponents have to be equal. So 4x minus 7 has to be equal to 4. Okay, and then you can solve this equation. And we'll do so by, we're going to add 7 to both sides. We'll be left with 4x is equal to, that'll be 11. And then I'll divide both sides by 4, and we obtain x is equal to 11/4. So we end up with another fraction. Okay. Alright. Now, let's take a look at the next example here real quick. What if we can't equate the bases? Okay. So for example, some of these down here. So if you look at example 4, this is, the base here is 84. Well, can I express 70 as 84 to some power? Okay. Well, no, not really. Not without using some irrational number. Okay. And so in a sense we can't really express, or we can't really equate the bases on these next 4 examples here. See right here, well, these have different bases to begin with, so but anyway, so what if we cannot equate the base? Then what do we do? Well, then we use logarithms. Okay. Now, I want you to think back for a minute how we've talked about how exponential functions are the inverse of logarithmic functions and vice versa. They're inverses of each other. Okay. So you can think of like an exponential operator and a logarithmic operator. Well, whatever one does, the other will do the opposite or undo. Okay. And so we're going to actually use logarithms to kind of undo what an exponential function does. Or in other words, similar to how you know, when you're solving a linear equation, the last step you do is divide both sides by some number, because the inverse of multiplying is dividing. Well, that's what we're doing here. So when we have an exponential equation like this, in which we can't equate the bases, then we're going to take the logarithm of both sides of this equation. Okay, similar to how you divide both sides of the equation by some number to isolate for x. If I take the logarithm, then I have to do it to both sides to keep my equation balanced. Okay, and then when you take the logarithm of both sides of your equation, you're going to be using one or more of those, well, one of those properties of logarithms, okay, to get access to that exponent. You'll see what I mean here in a minute. Okay, so you may be asking, okay, well, what logarithm do I use? You said that we're going to take the logarithm of both sides of this equation. What logarithm do we use? Because we've got an infinite number of logarithms. Well, in theory, it doesn't matter. It doesn't matter what base logarithm you use. However, because we do have easy access to the common log and the natural log, we will typically use either one of those. And I think I'm going to arbitrarily choose to use the natural log. Okay, that's what a lot of books will do, but I just want you to know that it doesn't really matter. You can use the common log or you can use the natural log. You can use log base 5. It doesn't matter. Okay. Alright, so I'm going to use the natural logarithm, which means I will take the natural logarithm of both sides of this equation. That's what this property is telling us right here. Okay, it says as long as you take the sum logarithm, as long as you take that log of both sides, then that will leave these arguments equal to each other. Or you can actually, you'd be going backwards. Let's say you have an equation like this, and as long as you take the logarithm of both sides of it, then it's still going to remain equal. It's still going to be an equation. Okay. Alright, well, where do we go from now once we take the natural logarithm of both sides? Well, we're going to use, namely, this property from 9.5, the power rule. If you recall, the power rule for logarithms allowed us to move the powers out in front of the logarithm. Okay, and so we do have a power here, right? The power is actually the variable x. So this is what allows us to get access to that variable. Okay, it ends up coming over here in front, and we end up with x times the natural log of 84 is equal to the natural log of 70. Okay. Now, let me say something. When you have the natural log of some number, this is a number, this whole unit right here. Froze again, unfortunately. Okay, and unfortunately I'm frozen. But let me highlight this for you. You want to start looking at the natural log of 84, the natural log of 70. Those are just numbers. Those are irrational numbers. Okay. So the way I solve this equation for x, I treat it, or I look at this like x is getting multiplied by this number right here, the natural log of 84. So to solve this for x, I need to divide both sides by this number, the natural log of 84. So you're going to be doing this a lot, guys. You're going to be working with these irrational numbers, okay? And so when you do that, the natural log of 84 divides out. That leaves us with x is equal to the natural log of 70 divided by the natural log of 80, okay? This is the exact solution right here. So you're going to, similar to when you're solving those quadratic equations, how you got a lot of weird looking numbers or solutions, well, you're going to get some weird looking ones here. This is an irrational number. Now we can approximate this. You can put this in our calculator. And I'll do that. You can type in the natural log of 70. Make sure you close those parentheses and divide it by the natural log of 80. And hit enter, and we'll get an approximation. If I round this to 4 decimal places, this will become 0.9695. 0.9695. All right. Okay. So, you know, when you're doing this, I would wait until the very end before I actually do a decimal approximation. If you try to approximate these earlier on, guys, then you end up incurring like some round-off error, and that can get multiplied as you perform more operations with those approximated numbers. So I would wait until the very end. Alright, let's look at example 5. So this one's similar, okay? There's no way for me to express 10 as 5 to some power. Okay, we know 5 to the first is 5, 5 to the second is 25, so I'm going to have to take the natural log of both sides again. And I'm going to kind of come over here to the right hand side. So I'm going to take the natural log of 10 to the negative x, and that will be equal to the natural log of 5 to the 2x. Okay, now again we're going to use the power rule, and it just basically says that we can move those powers out in front. Okay, so the negative x and the 2x. So this will become negative x times, you can even put an explicit multiplication symbol there to kind of help you remember. Times the natural log of 10, and this will be equal to 2x times the natural log of 5. Okay. Alright, so now I need to get my x by itself. Well, what you've got to realize is that this on the left hand side is one term, and this on the right hand side is one term. Okay. It's just that, again, the coefficients here, the numbers, are irrational, so they look kind of strange. In fact, you could sort of rewrite it. You could say this is the same as 2 times the natural log of 5, so that's like my coefficient of x. And then on the left-hand side, negative natural log of 10, that's like my coefficient for this x. Okay. And so I want to get my x's on one side of the equation. So I can either choose to subtract the right term, move it over to the left-hand side, or I can choose to add the left-hand term to move it over to the right-hand side. And that's actually what I'm going to do. I'm going to add natural log of 10 times x to both sides of this equation. And so when you do that on the left-hand side, you end up with 0 equals, and then I'm just going to rewrite this, 2 times the natural log of 5 times x plus the natural log of 10 times x. Okay. Now if these coefficients of x were integers, well, we would just combine these like terms, because these are like terms. However, it's a little tricky here, guys, because these coefficients are not integers. They're irrational numbers. And so the way we deal with this is we factor an x out of those two terms. And when we do that, that leaves us with 2 times the natural log of 5 plus the natural log of 10. And so in a sense what we're doing is we're combining those like terms. This is my new coefficient right here of x. Okay, and then this is equal to 0. And so just like normal, you know, when x is being multiplied by some number, you just divide both sides of the equation by that number. Well, in this case, it's this weird irrational number. Okay, it's all of this that's in parentheses. So we have to divide both sides by that. And so on the right hand side what happens is that weird, actually I wanted to use blue there. Well, I'll put my plus sign back together. I need to use red. That weird irrational number coefficient will divide out, leaving us with just x is equal to, and then over here on the left hand side, 0 divided by anything other than 0 is 0. Okay, so x will be 0, and so that is the solution to this equation. So a lot of this can become a little tricky or a bit confusing simply because these coefficients are these irrational numbers again. Okay, they're not the nice numbers that we're used to. But in any case, 0 is the only value of x that will make this equation work. I'm going to kind of partition this in that last one.
That was the shortest class I've ever had.
Oh, yeah.
Yeah, we got it.
All right, let's look at example 6 here. Very similar here, guys. You know, I've got a base of e right here, but there's no way for me to re-express 0.08 as e to some power. Okay, so I'm going to go about taking the natural log of both sides of this equation again. Actually, I'm going to zoom in a little bit. So I'm going to take the natural log of e to the negative 0.03t, and this will be equal to the natural log of 0.08. Now, in this case, choosing to use the natural log as our logarithm will actually benefit us a bit. You'll see how here in a minute. Alright, well, this exponent's going to come in front using power rule again. So we'll have negative 0.03 times t times the natural log of e is equal to the natural log of, well, that's 8/100ths. Now, interestingly, the natural log of e is 1, because remember, the natural log has a base, understood base of e. So e to what power is equal to e? E to the first power. Okay, and so you can sort of look at this like, well, the natural log of e is 1, so it's kind of like that factor just disappears. And so you're left with just negative 0.03t is equal to the natural log of 0.08. And now we're back to isolating for t again. Okay. Well, fortunately for us, the coefficient of t is not some weird irrational number. It's that decimal. So we'll divide both sides by negative 0.03. On the left-hand side, those coefficients divide out. This will leave me with t is equal to all of this. Okay. The natural log of 0.08 is one number divided by 0.03, and I'll get a decimal approximation for t. The natural log of 0.08 divided by negative 0.03, and we get, yeah, that's right. 84 if I were to round this to 4 places, this 9 would go to a 10. So this would become 84.1910. 84.1910. And that would be our decimal approximation. Okay. Real quick though, let me show you guys how you can verify this. If I go back to my original equation and I say e to the power of negative 0.03 times this number that I just came up with, and I'll just use the decimal approximation, 84.1910, and I hit enter, I'll get a value real close to this. This is not exactly 0.08, but you can see it's really close. Okay, The reason it's not exactly 0.08 is because I'm using this approximation for my solution instead of this actual number. This is the exact number right here. This natural log divided by this decimal. Okay. But anyway. Alright guys, well let's look at one more of these, and then we'll do a part 2 video in which we address solving logarithmic equations. Okay. So these would be equations that have logarithms in them. What we're doing here is we're using the logarithmic operator or function to solve these exponential equations. Alright, well this one's very similar. I'm going to have to take the natural log of both sides of this equation. So I'm going to come over here to the left. This will be the natural log of 3 to the power of 2x minus 1. Remember, all of that is the exponent, is equal to the natural log of 5 to the x. And so again, by power rule, these powers are going to move out in front. And this is where you want to keep that in parentheses, that 2x minus 1 times natural log of 3. And this will be equal to x times the natural log of 5. Okay. And now what I'm going to do is I'm going to distribute this natural log of 3 into these parentheses. Okay. And so this will become 2 times the natural log of 3 times x minus 1 times the natural log of 3 will just be the natural log of 3 equals, and then on this other side I'm just going to reverse the order. Okay, but again notice this 2 natural log of 3, that's just the coefficient for this term right here. And then the natural log of 5, that's just the coefficient for this x. So again, what I need to do, guys, is I need to get my x terms on one side of the equation. So I'm going to subtract this leftmost x term from both sides, and I have to do that by using a negative 2 natural log of 3. Okay. And so, you know, you can draw your bar like normal. On that left-hand side, these two terms will become 0. That'll leave us with just the negative natural log of 3 equals, and then on my right-hand side, I'm just going to rewrite everything. Okay. So again, we see an instance in which these again are like terms, so we can combine them. But because these are irrational coefficients, the only way we can really combine them is by rewriting this like we're taking the x out. So if you take out the x, then all you're going to have left is the natural log of 5 minus 2 times the natural log of 3. So it's like this is your new coefficient of x right here. And then this will be equal to the negative natural log of 3. And then just like always, our last step is to divide both sides by this coefficient of x. Well again, it's a weird irrational number, isn't it? Okay, so on the right hand side, that weird irrational coefficient divides out. That'll leave me with just x is equal to all of this right here, guys. This is the exact value of your solution. Okay. Now again, we can do an approximation for this if we put all this in the calculator. And so if I were to do this, I would type in negative natural log of 3, close with parentheses, divided by, open you a set of parentheses, and that's when you plug in this denominator, the natural log of 5, close that 5, then say minus 2 times the natural log of 3. Close the 3, and then you need one more parenthesis to close the denominator. Okay, and then hit enter, and this is our decimal approximation. 1 point, let's see, 4 decimal places would be 1.8691. Well, x is approximately equal to 1.8691. Okay, and then if you wanted, again, you could go back, plug this approximation in for these x's, and you'll get close to the same number on both sides. Again, it won't be exact because you were using an approximation, but it should be very close. I should have made myself more room for that one. Let me go back and fix my notes for that. Well, anyway, guys, so we've looked at equating the base to solve these exponential equations, and that's the easiest method if you can do it. And then we've also looked at solving them by taking the logarithm of both sides, and that's the more difficult way. Or equations that require that are typically more difficult, have more steps, and then you end up working with these weird, irrational numbers. Alright, well, I'll see you in part 2. We'll look at solving these logarithmic equations.